All right, let's jump straight into this briefing. If you've spent any real time working with power systems, you already know that fault analysis can feel like this massive, overwhelming catalog of rigid formulas, right? You've probably memorized one expression for a three-phase fault, a totally different one for a single line-to-ground fault, and then even more complex equations for line-to-line or double line-to-ground scenarios. And hey, that rote approach, it's fast. But it's only fast if every single thing is absolutely standard. The second your system topology, the grounding setup, the phase labels, or the actual fault impedance changes, the whole thing falls apart. It's a brittle mindset to have, and in power engineering, brittle is downright dangerous. So rather than relying on just memorizing equations, we're going to break down a highly structured, resilient method here today. Here is our roadmap. First, the fault analysis workflow, then the declaration ledger, sequence models and reduction, applying physical boundary conditions, reconstruction and verification, and finally, bounded evidence. Let's get to it.
Section 1. The fault analysis workflow.
There is a really stark contrast between rote memorization and having a true foundational understanding. Think about it for a second. When you rely solely on a memorized diagram, you can actually calculate a perfectly clean, mathematically flawless answer to the completely wrong problem. It's a huge trap. The math looks right, but the engineering is completely detached from reality. A much more reliable, defensible approach is using a disciplined, step-by-step workflow, one that actually adapts to the physical reality of the specific system you're analyzing. Okay, so what does that reliable workflow actually look like? Well, it's a step-by-step discipline that literally leaves zero room for ambiguity. Step 1, you declare the case and lay out all your assumptions. Step 2, you form the individual sequence models and reduce them at the specific fault bus. Next, you translate the physical fault boundary into sequence relationships and mathematically solve. But we're not done there. You then have to reconstruct the phase quantities, verify your results entirely independently, and finally, state exactly what your calculation establishes, and just as importantly, what it doesn't.
Section 2. The declaration ledger.
This is arguably the most critical point in any fault study. You have got to put every single controlling assumption right there in plain view before a single piece of arithmetic happens. You record the common power and voltage basis. You state the pre-fault positive sequence voltage right at the faulted bus. Freeze the phase order and sequence order so they don't magically drift later on. Define your current direction, name the faulted phases, and specify the exact fault location. But listen, the absolute most important thing? You have to define the exact physical path represented by the fault impedance. Why is that so crucial? Because a phase-to-ground path, a phase-to-phase path, and a common fault point-to-ground path do not enter the sequence relationships the same way. If you're just guessing here, your entire calculation is compromised from the word go.
You also need to be crystal clear about what your model is specifically leaving out. Like using a balanced pre-fault approximation, that might omit the pre-fault load current and just represent the system with steady-state sequence impedances. Now, for a textbook problem or a baseline study, that's totally fine. But remember, it is just an assumption. It is absolutely not a universal description of a live, operating power system. Putting these limitations on the ledger is what keeps your analysis honest.
Section 3. Sequence models and reduction.
Next up, we build the 3 sequence models, and we do this entirely independent of one another. The positive sequence network actively carries the pre-fault source, while the negative and zero sequence networks, those are typically passive in a standard balanced pre-fault model. Now, positive and negative sequence networks usually look pretty similar in their structure, but zero sequence, that requires totally separate physical reasoning. It literally needs an actual physical return path through grounded neutrals, transformer connections, and the surrounding network. If that physical path is blocked, the zero sequence branch is open. End of story. So carelessly copying your positive sequence one-line diagram over to your zero sequence is never, ever a safe shortcut. It takes distinct engineering judgment every single time.
Once those networks are built, we reduce each participating network down to the faulted bus. We call this fault bus reduction, and it gives us a compact set of driving point equivalents. Essentially, you get the positive sequence source alongside the positive, negative, and zero sequence impedances exactly as they are seen from the fault location. This reduction is a real game changer. By creating these equivalents, you neatly separate the really complex system modeling problem from the fault boundary problem. You boil the network down to its core elements right at the point of interest, which makes the rest of your analysis way more manageable and far less likely to turn into a sprawling mess of errors.
Section 4. Applying physical boundary conditions.
Okay, here is where we force our analytical models to meet physical reality. Let's look at the high-level differences between fault types. A balanced three-phase fault completely preserves system symmetry, meaning only the positive sequence participates. But a single-line to ground fault, that forces the two unfaulted phase currents exactly to zero, which tightly couples all three sequence networks together. A line-to-line fault has absolutely zero sequence current, so it only couples the positive and negative sequences. Meanwhile, a double line-to-ground fault can involve all three networks, but only if a valid zero-sequence return path actually exists. The physical reality always dictates the math, not the other way around.
The main takeaway here is that your network connection completely follows from the physical phase voltage and current constraints. The drawing you sketch on your page, that's just the result of those physical boundary conditions. It's not a substitute for them. When fault impedance is present, you have to go back to its strict physical definition and derive exactly where it belongs in your model. This is exactly where those notorious missing factors of 3 or misplaced impedances usually sneak into a calculation. You've got to let the physical constraints draw the analytical diagram for you.
Section 5. Reconstruction and independent verification.
All right, so after solving the core sequence equations, we have to shift out of the analytical space and back into the real world. We need to reconstruct the physical phase currents and voltages. And please remember this rule. Sequence current is not automatically the current in a faulted conductor. For example, in a standard ground fault, the faulted phase current actually contains 3 equal sequence current contributions combined. For a line-to-line fault, the total phase current magnitude comes from combining the positive and negative components. Reconstruction is that vital step that turns your pure analytical coordinates into the actual physical quantities you're looking for.
Then you absolutely have to verify your work, and this takes some real rigor. First, you check the reduced network equations themselves. Next, you transform your resulting phase quantities back into the sequence domain and make sure everything mathematically closes. Finally, you heavily test the physical fault boundary. You look critically for unfaulted currents that should be identically zero, check for faulted voltages that should perfectly match your previously declared impedance path, ensure equal voltages wherever phases are joined, and verify your current sum identities. Just remember, an answer that merely passes the formula used to compute it hasn't actually passed a true independent check yet. Always compare fault types on the exact same base, at the same bus, with the identical pre-fault state and declared network model. Consistency is everything here.
Section 6. Bounded evidence.
We have to be incredibly disciplined in how we interpret our final results. Yes, the largest current is highly system-dependent. Grounding and zero-sequence impedance can drastically shift the ordering of fault severities. Unfaulted phase voltages might also swing wildly during a severe unbalanced fault. But listen closely. Those are strictly analytical observations. They are not equipment verdicts. A purely phasor domain fault result does not magically set a protective relay, select a circuit breaker, establish an interrupting duty, or calculate an arc flash exposure. Those high-stakes decisions require entirely additional models, deep system data, strict adherence to standards, and highly accountable engineering review. A truly defensible answer makes that boundary explicitly clear.
To help build this exact discipline, you can leverage the MRK004 kit as a rigorous evidence loop. Try taking the diagnostic without any outside help at first. Genuinely learn the workflow and those deep fault relationships. Complete the challenge thoroughly before you ever peek at the verification pages. Repair the 3 flawed cases on your own. Attempt the transfer task completely independently. And then actually answer the oral defense questions out loud to really test your comprehension. Finally, track exactly what you can explain, formulate, apply, troubleshoot, and defend. The goal isn't just simple formula recall. It's about building a robust, fundamental fault analysis process that you can confidently reconstruct, check, and defend when the network inevitably changes.
So the next time you're facing a shifting network topology or an unexpected impedance, will you rely on a brittle, memorized formula or a defensible, step-by-step workflow? Thank you for watching. Keep building understanding, solve real problems, make better decisions.